is an RLC parallel circuit here. So the impedance looking here is, if it is Z, since this is parallel, you can say 1 over R, and if the inductive reactance is XL, then 1 over XL plus 1 over XC. So that's the capacitive reactance. So this one is the conductance, this is inductive susceptance, capacitive susceptance, like that. Now current, there will be the total supply current, we can say RS, and the current through resistance, if we say IR, IL and IC, the current through resistance, inductance and capacitance respectively. So IR will essentially be V over R, IL will be V over XL, and IC will be V over XC. So this one we can write V over J omega L, since that's the, and this one will be minus J omega C. So this is becoming, the current is becoming positive here, the angle, and if J is going over, so this is like that, this is the capacitive current, and this is becoming negative J V omega L, or negative J omega V. So basically 1 over Z, and this one is, and since this one is becoming J omega L here, and this is becoming minus J omega C, this is becoming 1 plus R, and if I rearrange this, this is becoming J omega C minus 1 over omega L. So this part is the capacitive susceptance, and this is the inductive susceptance, so it's just the inverse, and the sign is also inverse. So what we notice here is, if we look at the vector diagram, I will erase, I have to erase because I always run out of space, but you can remember that this is just parallel RLC, or you can just look back. So if I draw the vector diagram here, the current in this case is leading, so current IC, or current means I was talking about inductive current, is leading, and the capacitive current is going in this direction, IL. So this is negative J, this is positive J, and of course this is the real part, IR. So if say IL is, just for example, say IL is 5 milliampere, IC is 3 milliampere, and IR say is 5 milliampere as well. So the resultant IL minus IC will be 2 milliampere in this direction, and the vector sum will be the total current, which is IS. So this will be the total current which I can use, and this will be the angle. So angle theta will be, of course, this one will be IL minus IC over IR, tan inverse, of course, since in this right angle triangle, so this part will be IR, and this part, since IL is bigger than IC, so this is IL minus IC, and this is the resultant. So of course this angle will be tan inverse of IL minus IC. And if we notice that this is exactly similar to the power factor angle, or power factor, this is theta, and in power factor we used to say, I will just erase this thing, I will draw again. So let's say this one the current, and so here is IL, IC being greater than IL, and let's say this is IR. So if the resultant is somewhere there, this is the resultant, sorry, if IR is up to there, say IR is up to there, so, and this is up to there, then of course the this will be the resultant IS. So I'm just drawing arbitrarily. Similarly for power factor, when we used to talk about real power, we had real power, and we had volt ampere, and we had volt ampere reactive. Volt ampere reactive is the reactive power which corresponded to the capacitive or inductive power. Basically in normal load in an industry, most loads are inductive, so any motor is an inductive load. So what used to happen is, this is the real power, or just say let's power, and there was little bit of inductive power, and because of that we used to have a volt ampere reactive. So this is the var, volt ampere reactive, which is of course the hypotenuse of this right angle, and this is the volt ampere, which is the inductive power, IXL, I square XL, of course it's power, and this is I square R, this power. So it's the same angle basically, because it's corresponding to the current angle, just the magnitude is being squared. Now as we saw in power factor correction, a capacitive load was connected in parallel to reduce the inductive power, so that we could have a little bit of capacitive power there, opposite direction, so the resultant is less, and if the resultant is less, we would have a smaller amount of angle, and VAR will be closer to P. So P would be closer to volt ampere reactive, since theta is small, theta is close to 0, that was the target, and that would mean cos theta would be close to unity, close to 1, and that was achieved by applying capacitance in parallel to the inductive load. It's similar to that RLC circuit as we saw before. The RL, if we for a moment, if we forget the capacitance there, just the RL and there L there, we have an inductive load, but with the capacitance the total current is decreasing. And also we can notice one thing, that here also resonance is happening when omega C is equal to 1 over omega L, and when that's happening, it's again the same, the frequency, the resonant frequency is the same as the series resonance circuit. Only difference is, in this case, when the resonance happens, I will erase this part again, when resonance is taking place, so this is the inductance and this is the capacitance there. So when resonance is taking place, the IS is IR, because IL and IC will be opposite, and it will be like when IS is getting supplying, the capacitance is absorbing energy, the inductance is releasing energy. That's why they are doing it the same amount of energy, and that's why they are just interchanging energy. So the current drawn will be just the IS is equal to IR, and that's the resonant condition. So in resonance the current will be minimum. For parallel resonance condition, the current will be minimum at resonant frequency. So that's the thing. This is IS and that will be minimum. And also it's understandable from the 1 over Z thing. So it's 1 plus J omega C minus 1 over omega L. So this is becoming, this one is equal to that one. So omega C is equal to 1 over omega L. So this part is becoming 0. So just the impedance is just 1 over R, and so the current is impedance, not impedance, this is the admittance, inverse of impedance. So current is of course V over Z. So that will be equal to, basically this will reduce to R. So V over R as it was in series resonance circuit. So there is nothing difference in that sense, but only these two branches, the current, this current will be equal to this current for a resonance condition. So it's just pretty much the basic of very basic of parallel resonance condition.